Welcome. We are looking at the numerical solution for the diffusion equation, and we just looked at the Fourier transform based spectral technique for solving the diffusion equation, in which finally we showed that if you have Fourier transform of the composition field, this is spatial Fourier transform, then the time evolution is just given by dot t by 1 plus d k square delta t. Now, in this equation there is no boundary condition that we have implemented. That is because Fourier transform automatically implies periodic boundary condition. This is the reason why we discussed periodic boundary condition earlier. So, Fourier transform based techniques automatically assume that it is periodic boundary condition. So, the way the periodic boundary condition is going to enter into our calculation is in terms of this k. And as you will see in the implementation that I am going to show you, the implementation for the Fourier transform is exactly the same way in the earlier case where we implemented periodic boundary condition, where we said that if W which is the west point becomes equal to 0, then you replace it by W plus n. And the east point, if it becomes n plus 1, we said replace it by n minus 1. In a similar fashion, we are going to take the reciprocal vector and we are going to restrict it, and this is a common trick that you would have seen between minus half and plus half. Okay. So, sometimes it is pi by a, minus pi by a to plus pi by a. This is how periodic boundary condition is implemented in solid state, for example, or minus L by 2 to L by 2. This is how it is sometimes represented. So, we are going to use this whatever be the length, some minus half to plus half. That is the range of k values that we are going to keep. Anything goes outside, we are going to bring it back by either subtracting or adding, depending on whether it goes out at this end or it goes out at that end. So, this implementation of the periodic boundary condition is the only tricky thing that we need to care about when we do the spectral technique. So, let us write a small script which will solve the diffusion equation using the spectral technique. Okay. So, let us as usual go to the directory in which I am going to invoke Octave, okay, and I am going to open an editor which is a simple text editor. So, that is the gedit. So, and I am going to save a file, an OCT file. I am going to save it as remember, in the same directory in which you have invoked Octave is where you have to save the file, and I am going to save this file as implicit, because that is what we are going to do, spectral 1D diffusion.oct. So, it is implicit spectral 1D diff.oct. So, this is what I am calling my file. So, as usual, we first clear all the data, we clear the figure, okay, and then we say what is the number of points, and like I said, in Fourier transforms it is preferable to have it as a power of 2. So, n equal to 128. So, I am going to make a sinusoidal profile. So, that is as usual C zeros n comma 1, okay. So, it has put zeros everywhere. So, I am going to say m equal to 1. And then I am going to say for j is equal to 1 to n, what are we going to do? We are going to say C of j comma 1 is equal to 0.5 into 1 plus sine of what? 2 into pi into m into j divided by n far. Okay. So, let us put some comments here, so which will be helpful. Clear the memory and figure. So, define system size, so that is define system size, make an initial sinusoidal profile. So, that is what we have done, and it has a single wave. So, that is why m equal to 1, and I am going to plot the initial profile C with some red square boxes, okay, and then I am going to say hold on. Okay. So, this is plot the initial profile. Okay. So, after we do that, we are going to define, so for periodic BC implementation. So, we need to do certain things to get the periodic boundary condition implementation. So, I am going to define half length of the box. Okay. So, I am going to call it as half n is equal to n by 2. Okay. And then I am going to define the grid space. So, define this is define half length of the box. So, and then I am going to define the grid spacing in the Fourier space, okay, or reciprocal space it is called. So, how do we define? We say that del k, remember it is not del x anymore, it is del k is equal to 2 into pi divided by n. Okay. So, that is how we define it, and dt, which is delta t, is 0.5. So, to be consistent with our earlier notation, let us call it as del t. Del t is 0.5. This is the time loop. Okay. So, now what we are going to do? We are going to say for m is equal to 1 to some 200. Let us run for some 200 time steps. What are we going to do? First, we are going to take a Fourier transform. So, I am going to call this Fourier transform as C tilde, right. That is what we call in the analytical expression. So, let us call it as, so what is C tilde? It is fast Fourier transform of C. Okay. Then what do we do? For I is equal to 1 to n. So, we are going to go into the loop. In the loop, first we define, we implement the periodic boundary condition. What is, how is it done? If I is less than half n, then k is equal to, I times del k. Okay. That is n diff. On the other hand, if I is greater than or equal to half n, then what are we going to do? We are going to say k is equal to I minus n times del k, n diff. Okay. So, now we have defined k. I want to define k squared, or I can leave it as k, because we just need k squared. So, C hat of I, okay, comma 1 is equal to, what is it? We know that it is C hat of I comma 1 divided by, we have not defined d. So, let me go back and define the parameter d, where I defined n. So, I am going to say d is equal to 1, right, that is the diffusivity we assume. So, it is going to be d into k into del t, right, 1 plus d into k squared into del t. So, if you take the C tilde, so sorry, I should call it as C tilde, right, the Fourier transform is called C tilde by S. So, I should call it as C tilde. C hat is another notation for the Fourier transform. C tilde is equal to C tilde by 1 plus d k square t. So, now the C tilde that you have on the left hand side is in the new time. Okay. So, now if you end this for loop, so this end for is for this I loop. So, you have evolved it in time and you have ended. Okay. And now you can keep doing it for the number of steps, that is n for this is for the m loop, which is the time loop, and finally when you come out you need to take the inverse Fourier transform. So, IFFT, so now let us get back to C. C is equal to IFFT, which is inverse Fourier transform of C tilde, right. If you take C tilde and do the inverse first Fourier transform, you will get the C, but we only need the real part because C is real. So, let us keep it only to the real, because when you do Fourier transform it has real part and imaginary part, and C we took as real. So, it went, and then when it comes back, because of numerical errors it might have collected some imaginary part, but that is not part of our solution. So, let us remove it. After you do that, plot C, right. So, there is a hold on that I introduced, I suppose. So, this will plot on the same plot what the solution is after you evolve it for 200 time steps. Okay. So, that is what this code does. Now, let us try to go back and run this. So, for running I have to say source, this is an implicit one, I think Spectral is what I called 1D diff dot OCT. Okay. So, as you can see I get the solution, but I do not see the evolution. So, maybe I need to run for longer time to get the evolution. So, let us run it for let me run it for longer time. So, let me run it for some 20,000 time units, and that is going to take slightly longer to run. I will just start the calculation, we will look at it later. So, what we are doing, trying to do using Fourier transforms is very simple. You know, it has again become an algebraic expression. You did a Fourier transform on the variable, and then you went to the partial differential equation, you found that it can be reduced to an ordinary differential equation, and now we are trying to solve that ordinary differential equation. And when we solve this ordinary differential equation, so it is an implicit method. So, it is quite simple, unlike the case of finite difference technique, where implicit method actually involves solving a set of algebraic equation by doing some matrix inverse and multiplication and all that. In this case, that has simply become an algebraic expression, as if it is like an explicit method. So, then you can directly solve the equation and you can plot the solution. And now, as an exercise for this problem, I would like you to try several initial conditions. So, let us list them out, and for example, you can take an initial condition in which you take 1/3 of the distance to be 0, another 1/3 here to be 0, and the remaining 1/3 to have a value of 1 for composition. So, this is one initial condition for which you can try. See, remember, because Fourier transform assumes periodic boundary condition, your initial profile should be periodic, if not it will not work. The second thing that you can do is that you can take some constant C naught, let us say that is equal to some 0.5, and you can put some noise about 0.5, okay, some random noise about 0.5, and you try to evolve the system. Of course, you know that all the noise should die down and it should become a constant after a long time. So, these are a couple of problems that one can solve using the spectral technique given the code. So, you can take the script, you can modify it, and you can try to solve these cases. So, that brings us to the end of this section. So, let us remind ourselves what is it that we have done. We have looked at the diffusion equation, we looked at its solutions using analytical means, We have also looked at its solution using finite difference technique and Fourier spectral technique. The next step is of course to go do the same thing with the Cahn-Hilliard equation or the phase field equation, which is a nonlinear diffusion equation. For doing that, we are going to stick to the spectral technique. I am going to spend most of my time trying to do spectral technique. Maybe for some 1D problem, we will try to do the finite difference technique, but you will see why finite difference becomes too messy for solving an equation like Cahn-Hilliard equation, which is nonlinear. So, we will solve primarily using a spectral technique, and it's fairly easy to solve in 1D. And what we haven't done and we will do as part of tutorial for the course is to solve the diffusion equation in 2 dimensions, because using Fourier transforms, we are going to solve things in 2D as far as the Cahn-Hilliard equation is concerned. So, it might be a good idea to try to solve the diffusion equation at least in 2D and see how the solution looks like and things like that. And then we are going to solve the Allen-Cahn equation and then combinations of Cahn-Hilliard and Allen-Cahn. So, that takes us to the phase field part, but before doing that I need to show where the phase field equation comes from. So, we are going to do a little bit of mathematics to derive the Cahn-Hilliard equation. I did not derive the equation earlier, I just wrote down the equation, but deriving the Cahn-Hilliard equation involves a little bit of mathematics. It involves a Taylor series expansion, which is in multiple variables, something that some of you might have seen, but it is not very common. After you expand the free energy, it is a free energy functional because it consists of both the composition and its gradients. So, the Taylor series expansion is in terms of composition, its first gradient, second gradient, third gradient, etc. So, those are known as gradient, curvature, aberration, etc. So, in terms of those we are going to expand the free energy functional. When you expand, you will see that the free energy functional consists of lots of property tensors. So, we need to understand tensors and how to deal with the tensors and what kind of properties they have to obey for representing the underlying symmetry of the crystal that you are considering. For example, what happens to these tensor quantities if you assume that the system that you are dealing with is isotropic or cubic. We might not go in this course beyond cubic, but we will indicate ways in which you can go beyond cubic systems. So, you can say that how to deal with cubic anisotropy, for example, the underlying crystal is cubic. So, what happens to the tensors, and in terms of then those properties, then you can reduce the free energy functional to a simpler form, and that involves some Gauss-Green theorem kind of theorems, and once you have reduced it, then we need to look at the chemical potential. So, chemical potential can no longer be derived as a partial derivative, but it becomes a variational derivative because we have a functional instead of a function. So, how to write variational derivative becomes an issue. So, once you have written the variational derivative and you get the chemical potential, then we need to substitute it in the modified Fick's law that we said that the flux is directly proportional to chemical potential gradients. And once you have done that, to get to the time dependent part, then we will use the usual arguments and write the evolution equation, which becomes the Cahn-Hilliard equation. And in the case of Allen-Cahn, I am just going to write the free energy functional, and directly I am going to show you what the evolution equation is, because in that case we assume another type of constitutive law to get to the evolution equation directly. Okay. So that is the part. So, that involves a little bit of mathematics. So, the next several lectures are going to be on these mathematical topics. They look disjointed because I am going to talk about certain mathematical entities and their properties and how they behave, etc. Then I will move to the next mathematical entity. So, we will keep doing this, but once when we come back and try to derive the Cahn-Hilliard equation, they will all fall in place. Okay. So, the next few topics are going to be mathematical topics, but there is no continuity that you can see at this point for these topics, because they are not really continuous things. I mean, they are different mathematical aspects, but we need all of them if we want to understand Cornelian equation. So, we are going to do these bits and pieces of mathematics, and then we are going to come back, put them all together to derive the Cornelian equation, which we will do from the next lecture onwards. Thank you.